So here's my latest project, which is a simple heart rate monitor using a reflective sensor. The reflective sensor I'm using is the TRC T5000, which is simple, cheap yoke. Has infrared LED and phototransistor, and you get like 10 of them for €1 off eBay. The way this works is like any other pulse oximeter which you've probably seen in a hospital. So I'll just turn this on there. See a flashing light in there, that's red LED, and there's a flashing infrared LED which you can't see on the camera, and there is a photo transistor or an LDR down at the bottom there which you can't really see. So the way it works is the amount of light that reaches the light sensor changes depending on if there's blood in your finger or not. So as blood passes through your finger, the light or the output from the light sensor will pulse along with your pulse. So from that you can calculate your beats per minute. Another thing these do is the oximeter part, measure your oxygen levels. So to do this you need two LEDs, usually use a red and an infrared. Here I only have an infrared. I was going to use the two, but a problem with this sensor is the phototransistor blocks visible light, and red light is on the visible spectrum, so shining red LED on it made no effect to the output. So I'll just quickly explain how you measure the oxygen levels. So the way this works is it flashes the red and infrared intermittently. One's on, then turns off, the other one's on, then turns off, and it just cycles through them. And then because the amount of light that passes through oxygenated blood for each of the infrared and red light is different, you can take the ratio of how much light passed through when the red was on and how much light passed through when the infrared was on, and that can be used to measure the oxygen levels. But I won't be getting into that because I couldn't for this circuit. So I'm just going to quickly explain this. So we're using a few op amps. This is our supply. I'm supplying it with 12 volts. This is being paired off a single supply. This op amp is being used as virtual ground. So if you wanted, you could pair this off set of batteries. You don't need to pair with two separate supplies. This potentiometer here is working as our low pass filter, and that changes cut-off frequency of it. And if you want to check how much it's being filtered, you can put a probe onto this yoke here. This other potentiometer here is changing the gain out of our final amplifier, which our output's coming out of. And here is our virtual ground, and this is our output. Both of these are being connected to an Arduino Nano with a very simple circuit, which is kind of working in an oscilloscope. So this brown wire here, that is going into a capacitor that is filtering the DC out of our output signal. So we only have the AC coming out of it. We don't want any DC offset. We want to control that later. This potentiometer is working as a voltage divider, so we can reduce the amount of voltage going into the A to D of the analog input of the Arduino Nano, because that reads in 0 to 5 volts. If this can go to a max of 6 volts, it'll just clip on our little oscilloscope code on here if it's at actual 6 volts, so we need to reduce it. And this other potentiometer here, that is a DC offset which we can control. Because we're taking out the DC offset, the negative parts of the waveform won't be seen on the oscilloscope, so we need to push it up with our DC offset. So I'm just going to take my pulse here, see what it says, and then I'll show you my processing code for it. So 90. I have some medication which is kind of increasing my heart rate, but from this project I noticed I should probably do some more cardio. So 90 is the number we're looking for on our code here. So this is the processing code and Arduino code. Both of them will be on my blog, which will be in the description. So we'll just hopefully this works first time. Okay, our output's a bit very small, so I'm just going to stop this video because I would need a third hand to change the potentiometers. So we're going to join back to this in a minute. So we're back in. I just need to change the gain of the potentiometers so I'd get a better signal on the graph. So now the code is processing my heart rate, which jumps up and down. It isn't exactly accurate, like the pulse oximeter would be much better. And I'm just going to press our record button now, and you'll see a problem with this code. I'm going to lift up my hand, and we'll press here. It's recording now, but it's recording old data. It's not able to do a real-time graph. For the life of me, I couldn't figure out how to get processing to read in the data fast enough and graph it. So right now, oh, we're getting a bit weird now. Yeah, it's alright now. So yeah, there's a delay in between the actual output of the nano and what we're seeing on screen, and as longer you record, the longer that delay gets. Let's just stop recording now. So I'll just show you what that did there. So that is going to be saved into here. I'll just give you a quick look at it. And you'll probably see, oh, that's finally caught up with my finger coming off it. Where's our X out? Just quickly graph this, right? No, don't do that. So that is what we just recorded over that few seconds. Just going to zoom in a bit, change the x-axis. So there we go. So if we actually measure the time between the peaks, you get an accurate representation of the pulse I was having at that moment in time. But for some reason the code isn't as accurate as just finding that peak and that peak. The peak detection could be improved. There is problems with it. If the peak is flat, it doesn't recognize it and just skips over it. So you have half the pulse that you actually do, or that's what it calculates. So anyway, so I do know you can read in the values fast enough because the serial plotter in here can do it. So I'll just show you now. We'll go into our serial plotter, and see now, this is a real-time graph of my pulse, and I'm going to take off my hand right now, and notice it. I'm going to tap on the sensor, and we have that. Take my hand away, put my hand back. So it's sampling at 100 Hz, and the serial plotter is able to keep up fine. And I've tested at 1000 Hz, and it's able to keep up fine. But I don't know why I couldn't get the processing to keep up as well. But I'm going to put up the code for the Arduino and the processing, and if anyone can actually tell me how I could get the processing sketch to read in real time accurately at like 1000 Hz, that'd be great, because the more samples we take, the more accurate we can get our pulse rate calculation to be. And see there, still keeping up, so I'm just going to close that. So anyway, even though I couldn't get a real-time graph working, I think it turned out pretty well. Like, I got this working, and have a mini little oscilloscope code working here. So yeah, if you want to see the code and circuitry and calculations I had for this project, you can visit my blog at roboroblog.wordpress.com. And thanks for watching.